So welcome to Chapter 9. This is video number 1. We're going to take a look at what sound is, how our ears detect sound, and then how the brain processes that information that the ears bring into the nervous system. So we'll start off with what sound is. It's actually a physical stimulus. It is the result of what happens when our voice or our hands, for example, displace air around us. And so any sound that we hear, it is because there's some object or something there that is moving and displacing air. And that has an interesting effect. So to understand how the physical stimulus for hearing works, we can use an example of someone clapping their hands, right? So before the clap, we can see up here that all of the air molecules are kind of evenly spaced out. So each of those red dots is representing an air molecule. And so, yeah, they're all kind of evenly spaced out. But here, where the person starts to clap, we can see that the disturbance in the air sort of pushes some of the air molecules together, sort of squishes them together. And then, because there are only so many air molecules in this area, the space around it ends up having fewer air molecules. And this disturbance travels through the air so that there'll be spaces where the air molecules are all kind of scrunched up together, and then spaces where they're sort of spread out, and then another space where they're together, and then another space where they're spread out, and then again together, spread out, together, spread out, and so on. And because this cycle of the air molecules being sort of compressed or spread out, also known as rarefied, we get this pattern where the air molecules convey sound in the form of what are called sound waves. And it's just this repeating pattern of the molecules in the air being compressed together and spread apart as a result of the disturbance caused by the clapping hands. And so we'll see that that sound wave, which is the physical stimulus, travels to the ear where the receptor is. The receptor, we'll see, is called a hair cell, and there's many, many of them, so hair cells. They create the neural signal, and then that ends up going, of course, to the brain. Now let's talk a little bit about the difference between sensation and perception. We sometimes take these, as being interchangeable, but they're not. Sensation is literally the detection of a physical stimulus. It's your hair cells detecting the sound wave. That is what sensation is. So a good synonym for sensation is detection, that your hair cells detected the sound waves. The perception part actually happens much later, and that's what happens in the brain. Now let's take a look at how the sound wave conveys information about the pitch and the loudness of the sound. Now we can think of the pitch corresponding to the keys on a keyboard, for example. So a low-pitched sound would be this, whereas a higher-pitched sound would be this. A lower-pitched sound wave is made by using a lower frequency. So let's take a look at these two sound waves. They are the same height, just about. But notice if we look at the number of peaks in this short segment here, in this sound wave, there's only two. 1, 2 in this sort of zone. And the one in the bottom, we can count 1, 2, 3, 4, 5 in the same amount of time. So if this was, for example, a fraction of a second, like say a half a second, and this was half a second, this sound wave at the top would have 2 cycles per half second. This one at the bottom would have 1, 2, 3, 4, 5 per half second. And so that would mean that the bottom one would produce a higher pitch sound, and the top one would produce a lower pitch sound. In contrast, the loudness comes from the amplitude of the sound wave. And the difference in amplitude is contrasted here between the top sound wave and the middle one. The top one has a much larger amplitude. That sound is going to be much louder than the bottom one. Notice the 2 sound waves shown here, the top one and the middle one, have equivalent frequencies. They would be the same note on the piano, for example, but the top one would just be louder. The bottom 2 sound waves would be just the same loudness, but different keys on the piano, with the bottom one being a higher pitch key. So that's the difference between amplitude and frequency, and how the sound wave provides information about those 2. Amplitude corresponds to loudness. The frequency corresponds to pitch. Now notice that we see here this notation here of hertz. Hertz refers to the number of cycles per second, and it's a way of quantifying the frequency of the sound. So humans can hear sound waves that are between 20 hertz and 20,000 hertz. So that would be 20,000 waves per second would be our high end of the frequencies that we can hear. In textbooks, you often hear about pure tones. Pure tones don't really occur in nature. They are sounds that consist of a single frequency, just one frequency. So like here, A is a pure tone, B, C, and D are pure tones. Here's a pure tone of 100 hertz. Here's a pure tone of 500 hertz, just about. We'll do 1,000 and 2,000. And I won't torture you with anything higher pitch than that. Real sounds played by like a musical instrument, or by a human voice, or a bird chirping, or whatever the sound might be, are usually made up of complex sounds that are a combination of a variety of frequencies together. So again, like a pure tone just does not exist in nature. So here we can see the range of frequencies that humans can hear. We have here the auditory threshold. That's the minimum loudness necessary for a person to detect a sound, and we have that indicated here in this line. So everything where the dotted lines are, we are not, a person of typical hearing, normal hearing, would not be able to hear that. And so you can see that really the cutoff on the low end is 20 hertz. That would have to be really loud, and it would probably just sound more like a vibration. So, you know, at less than 60 decibels, which is how we measure loudness, decibels, we would not hear it. Now, as the frequency goes up to 100, it would have to be a minimum of 30 hertz for us to be able to hear it. Sorry, 30 decibels for us to be able to hear it. And then as it goes up to 500, we would be able to hear it even if it was only at about 20 decibels. We are most sensitive to sounds that are between 1,000 and 5,000. So we can hear those when they're very, very low, which is handy because that is the set of frequencies that make up the human voice, and it allows us then to hear, you know, whispers and to hear humans speaking even if the volume is not very loud.